So we have assumed this basically. We now have to prove x is equal to x prime and y is equal to y prime. Oh, sorry, I have to be very careful about writing these things. Okay, their meaning changes completely if I forget something. Okay. Now okay, now cases arise. Okay, so what is the first case? The first case is that x is not equal to y. Or let us deal with the easier one. Assume x is equal to y. Suppose x is equal to, exactly two cases will arise. Either the objects that we have assumed, x, y, there are x prime and y prime also, but let them be. They are either the same object or they are not the same object. So first of all, we are assuming that they are the same object. Then what happens to this set? Since x and y are equal, we have this. Keep in mind that in sets we don't repeat elements. So that's why we are able to simplify this. And similarly, oh no, we can't say that. Wait. I was going to write something with similarly with x prime and y prime, but I can't say that since this assumption is only for x and y. We thus have so what do we have now from this whole thing? x prime comma y prime is equal to x. How many elements are there in this set? Apparently there are two elements. However, in this set there is only one element, which is itself also a set. So since they are equal, this set also must have only one element. That means both of its elements have to be equal. So this implies x prime is equal to x prime comma y prime, and then using the same logic, this set also is a singleton set, so this must also be a singleton set. This implies this, which in turn implies we must have x prime is equal to y prime. So x is equal to y, x prime is equal to y prime. Okay. We now have, so what the left hand side becomes ultimately, looking at this simplification, we can now do the same simplification because we now have the same similar condition here, x prime is equal to y prime. So this will be equal to from which we get x is equal to x prime. So see, we have got x is equal to x prime. So now y will also be equal to y prime, because x is equal to y and x prime is equal to y prime. Hence y is equal to x, that we are getting from here, and x is equal to x prime, we have got it from here, and x prime is equal to y prime. So what we have done, we have assumed that this ordered pair x comma y is equal to the ordered pair x prime comma y prime, and we have concluded that x is equal to x prime and y is equal to y prime. So that is the other half of 3.5. In the case when x is equal to y, now we deal with the case when x is not equal to y. But before that, let us just conclude this. So we have proved this. Implies when x is equal to y. It's a good practice to make small conclusions in the middle of a proof, so that you don't lose track of the things. When the proof gets very long, looking at it, you won't be able to distinguish between the parts. So it's better to write some conclusions, and so the job is done here for this part. Now next, assume that x is not equal to y. Okay. So now if x is not equal to y, what can we conclude from this? Right? Okay. So if x is not equal to y, that means this is not equal to this. Then this is not equal to x comma y, because this set has one element and this set now has two elements. From this condition we get that. Hence our assumption now implies what? This is not equal to this, so that means this set has two elements. One of them is this set and one of them is this set, and they are different. So this set has two elements, so likewise this also must have two elements because they are equal. Hence this implies so this implies what? X prime is not equal to x prime comma y prime. Okay, and that further implies, using the same logic, which in turn implies that x prime is not equal to y prime. So you see, in the previous case when we assumed that x is equal to y, we got also the fact that x prime is equal to y prime. Here we assumed x is not equal to y, so here we are getting the fact that x prime is not equal to y prime. So whatever happens on one side, a similar thing happens on the other side also. Okay. Now given that x and y are different, x prime and y prime are different, what can we conclude from this? That we have to figure out. ultimately our aim is to show that x is equal to x prime and y is equal to y prime. Okay. Since this is an element in this set, it must also be an element in this set. This must belong to the second set. So that means this element is either equal to this element or this element. Note that we cannot have this equal to, since two elements this is a set, this is another set, this has two elements whereas this has one, that's why they cannot be equal. And where is this fact that this has two elements coming from? That is coming from this. Okay, x prime and y prime are different. So we must have there is no other choice. This is an element in this set and it's not this element, so it has to be this element, which implies x is equal to x prime. A similar argument makes us conclude this. Whatever we have done with this element or this set, this element of this set, we can also do with this element, which is a set with two elements. And since this element belongs to this larger set, it also must belong to this one. However, this set cannot be equal to this singleton set because it also has two elements, and that is coming from our assumption x is not equal to y. So it has to be equal to the other thing. Note how we are using the fact that the objects are ultimately different to conclude all these things. Okay. Now, since x is not equal to y, x prime is not equal to y prime, and y prime belongs to x comma y. See, y prime is an element in this set, so y prime must also be here, but y prime cannot be equal to x. Okay, I must mention one more thing. X is equal to x prime and y prime belongs to x comma y. We must have y is equal to y prime. You see what we have done here, y prime belongs to this set, so y prime must be here. So either y prime is equal to x or y prime is equal to y. If we assume that y prime is equal to x, then y prime will be equal to x prime also, because x is equal to x prime. But then y prime, okay, then this is contradicted. Okay, so that's why y prime cannot be equal to x, y prime has to be equal to y. So again, in this case also, where we have x not equal to y, we have proved, again we have proved this. So again we have proved implies x is equal to x prime and y is equal to y prime if x is not equal to y. So 3.5 has been proved in its entirety, and that's why we can use this definition of an ordered pair as a legitimate definition. Note one thing, see how cleverly we have generated order from a concept which does not respect order. I mean, in a set there is no order. In a set we know that elements, order of the elements in which they appear, that is not important. So how can we distinguish between x and y? X is the first component of this object, y is the second component. They have done it by considering x and y to be two different elements of these two sets. I mean, I should not say different element, but status of x and y are different in this set. In what sense? You can distinguish between x and y like this from this definition. X is that object which appears in both the elements as an element, and y is that object which appears in only one of the elements. Okay, so that's how we created order, or rather a way of distinguishing x and y. And also there is a first and second. The first coordinate is that element which appears in both the sets. The second coordinate is that element which appears in only one set. So this definition is actually quite clever. The mathematicians have not just simply sat down and wrote whatever they wanted. There is a reason why this definition looks like this. However, it can be slightly changed by not requiring a set here, but simply taking the object itself. This new definition we will show that also will satisfy 3.5. However, the proof will be somewhat more complicated. Now what is the job? So our definition of ordered pair is okay. We now have to show that using this definition we can make sure that if two sets x and y are given to us, then their Cartesian product is also a set. Now we will prove that. Okay, so let us see that part of the proof. So we can first of all deal with the case where at least one of the sets is empty, then the Cartesian product will be empty. So this part of the solution goes like this. We now show that for two given sets, x and y, the Cartesian product is also a set, but only using the axioms of set theory that we have so far got. If at least one of x or y is why do I keep saying non-empty, is empty, then from our definition of Cartesian product that we have in the section, that is definition 354, this is empty. So in this case, definitely the Cartesian product is a set, because from our second axiom of set theory we know that there is a set known as the empty set, which has no element at all. Okay. So now we assume that both x and y are non-empty. Right? So now fix an element y belonging to any element, but we are fixing that element. We are not going to change that. We have not going to change for the time being. We have fixed it, and now we are going to work with this element for some time. Okay, now what we are going to do, we are going to define a statement that depends on two objects. For any objects u and v, and any element x belonging to x, consider the statement p x u v, and the statement is this: u is equal to x and v is equal to y. This may seem like quite a strange thing to do suddenly in the middle of this proof, but actually why are we defining a statement like this? We want to use the axiom of replacement. Do you remember the axiom of replacement? Suppose we are given a set, okay, and for every element in this set and every object y whatsoever coming from where we don't know, there exists a statement p x y that depends on this element and this object, and this statement satisfies one condition. That condition is that for every x in x there is at most one object y for which this statement is true. Then the axiom of replacement says that if we collect those y's such that p x y is true for some x belonging to x, then this collection is itself is a set. So here what we are doing is that we are replacing x with y. So that's why it's called the axiom of replacement. And we have in fact used this axiom to show or say that images of functions are actually sets, things like that we have already done. So here again we are going to use the axiom of replacement. In place of this set X, we still have X, and in place of its element X, we have X. Now in place of Y, we have an object that looks like this, an ordered pair U comma V, where U and V themselves are some objects. Okay, so this is an object coming from somewhere in the universe, and X is coming from this set, and our statement is this, which depends on this X and this object Y. Okay, don't confuse this Y with that Y. This is the axiom of replacement separately. Now this is our actual statement P. Whether that condition is true for this statement, that for a given object X, given element X in X, there exists at most one object U comma V for which this is true. Actually that is true. In fact, not just at most one U comma V, exactly one U comma V, namely that U comma V which is actually X comma Y. So this is a situation where we can use the axiom of replacement, and we will be replacing X with Y. In our case, that Y is U comma V. So you see that we are replacing an ordinary element by an ordered pair, and that set of ordered pairs, that collection of ordered pairs will be a set. Note that for each X belonging to X, there exists exactly one. Exactly one means almost also at most one. Exactly one U comma V for which this statement is true. Namely, what is that U comma V? X comma Y, because then U is equal to X and V is equal to Y. So by the axiom of replacement, I think it is axiom 3.5, but I don't remember exactly. Let us just use the name. The following collection is a set. Okay, and to make it more clear, I can in fact write it like this. Or wait, hold on, it's not X comma Y, U comma V such that P of X comma U comma V is true for some X belonging to X. So this is, we are directly writing the collection as it appears in the axiom of replacement. For our P, we are considering the objects by which we are replacing x. We are replacing x with u comma v, such that this is true, and this turns out to be equal to nothing but this collection. And we are denoting this collection by this symbol x suffix y. Y is denoting the fact that we have chosen this element y from y. So do you realize what this is? It is the collection of all ordered pairs where the second coordinate is, or second component is y. Okay, and x is varying, the first component is varying. Now if we do this for every element in y and take the union of such sets, then we get x cross y. You can understand. Okay, so this is a set. Now using the axiom of replacement, once again we get the set What are we doing when we are saying we are again using the axiom of replacement? What what we have, for every y in y, we now have this set. So we can consider the collection of such sets x, y, where y is varying over the set capital Y, and this collection itself is a set. So on this set we can now apply the axiom of union. We can take the union of all the sets in this collection. Remember that axiom. That axiom says that if we have a set whose elements themselves are sets, then their union can be taken, and that itself becomes a set. So to be able to use the axiom of union, we need the fact that the collection of sets that we are considering is itself a set. So here we cannot, for example, consider the collection of all sets, because that is not a set, to take their union. Okay, and that axiom of union is specifically axiom 311. So by axiom 311, the union, if you go to the axiom of union, you will understand the meaning of this notation. It's nothing but the union of all the sets x, y. The union is a set. Note that this union is nothing but the Cartesian product x cross y. So we have proved using the axioms of set theory that the Cartesian product of two given sets is actually a set. So what we have done here, we can show you with a very simple example. So if we have 3, say, if we choose our y to be 3, then x3 is this 1, 3, 2, 3. It's the set of those ordered pairs where the second component is 3. And in place of y, if we have 4, then we have x4, which is 1, 4 and 2, 4. So if we take their union, one, 3, 2, 3, 1, 4 and 2, 4, then this is nothing but x cross y. So that's what we have done basically. Okay, and now the solution is not over. Now we have to go to the challenging part, where we have the second definition. For that also we have to show, just like we did for the first definition of an ordered pair, that condition 3.5 is still true. Now we consider the alternate definition.